here with Dr. John Mather. Dr. Mather is NASA's Goddard Space Flight Center and 2006 Nobel Prize winner in physics. Dr. Mather is one of our plenary speakers at Advanced Imaging and Optics in Arlington, Virginia. In his presentation, he outlined the mission design of NASA's James Webb Space Telescope, planned for launch in October 2018. Dr. Mather, the Hubble telescope celebrated 25 years last month. What has been the greatest takeaway from its research?
Well, the Hubble has discovered some totally amazing things that were definitely not expected when it was being designed. I think the biggest surprise for astronomers was that we were completely wrong about how galaxies form. A galaxy like the Milky Way is 100 billion stars orbiting a common center, and prediction was they formed very recently because it's such a big thing. How could it happen quickly? The Hubble telescope took pictures that showed that happened almost right away, beginning soon after the Big Bang. So, and they showed us that there were galaxies forming far, far, farther away, and even the amazing conclusion from that was Hubble would not be able to see far enough to see the first galaxies being formed. So that was a big surprise. Number two, they found there's a black hole in the middle of almost every galaxy. So a black hole is found because there's so much concentrated gravity that things go whizzing around extremely fast when they're right near it. So they were able to measure the speeds of motion of stars orbiting the black holes using the spectrometer in the Hubble Space Telescope. So galaxies very young, formed very early, and have black holes in the middle. We were able to see that the universe is accelerating. This was a huge surprise. In 1998, was found that distant supernovae, which are sort of like standard candles, are about 20% fainter than they should have been. So 20% is a big deal, and it means the universe had to be different than we thought. So the explanation is it's been speeding up over time, and that's why they're farther away than we thought. So we call it dark energy, and we have no idea what that dark energy is. Another wonderful surprise is we were able to study the chemical composition of planets around other stars. So this is done by the transit technique. If a planet goes between the star and the telescope, it blocks some starlight. Some of the starlight goes through the planetary atmosphere on its way into the telescope. We can measure that difference, and we can even measure the spectrum of the difference. So we can say, okay, what are the molecules in those atmospheres? So this has already shown us several different ones, and we expect it to be very powerful in the future with future telescopes. So those are some of the biggest ones, and there are many, many more. But of course, always the greatest surprises are the ones that you didn't even think were going to be there.
Fantastic. The James Webb Space Telescope utilizes high-performance imaging optics to see beyond what the great Hubble telescope can see. Can you explain the differences to those not familiar with the program?
Okay, well, the main differences are that Webb telescope can be able to observe infrared light. So the Hubble goes from ultraviolet out to about 1.7 microns wavelength of infrared. The Webb telescope begins at 0.6 microns and goes out to 28 microns. So it's a huge difference in what they can see. They do overlap a little. So the other big difference is the Webb telescope is much larger, so it can see farther because it's more sensitive. So the combination of these two things enables us to say we'll be able to see farther back in time, farther away in space, to see the first galaxies being formed after the Big Bang. Maybe to see the first black holes being formed, however they may have formed, we don't know. We'll be able to see inside star clouds where stars are being born today. Usually that's hidden by the dust that's in front of us, but the infrared light has the ability to go around a dust grain instead of bouncing off it. So that means we can see inside the cloud to see stars being born. Closer to home, I looked at to see how does the solar system work and how do other planetary systems work, because we'd like to see how come is Earth special. Earth is special. Earth has an ocean, Earth has continents, Earth has a big moon, but how did it get like that? So studying our own solar system is a way to get that at that part. So in particular, how did the Earth get wet? Early Earth was probably dry and hot, so where did the water come from? I'd like to find out.
In 2015, we're celebrating the International Year of Light. Can you tell me where you think optics and photonics will be going in the next 20 years?
No, I can't, but I love to speculate. So I think we're seeing a tremendous improvement even in classical imaging. We have better optical designs. We have ability to make huge cameras that can see everything at once, that can stay in focus focus everything at once using advanced computational techniques. We just heard about that today. I think there's a lot of room for improvement in classical optics. There's tremendous progress with fiber optics and what we can do with that, ranging from sensing things that we didn't think we could sense before. I can imagine a day when we have fiber optic sensors that you can that a surgeon might use. Thread a little fiber and we won't even feel it, and the surgeon will know how we're doing inside. Well, we're certainly using lasers to control individual atoms. We even use in science now, we can use a laser to split an atom into two pieces and bring it back together again in an interferometer technique, which is similar to what we use in optical interferometers. But now, because atoms have inertia, they can pick up gravitational forces and they can pick up acceleration and other things that are interesting, not just for their own sake, but because we can use them to sense things. So we can use them to sense whether the Earth is changing its shape because the water is moving around. As it does, the ice caps melt, the water flows, oceans go up and down. We pull the water out of the ground, the rain fills up the lakes. All these things change the gravitational field of the Earth. So we can measure that, and we can do it with atom wave interferometry. The sort of holy grail in astronomy projects is, well, how about detecting gravitational waves from merging black holes or merging neutron stars? And a technique for doing that could also be based on atom wave interferometry. So there's sort of no end to what you can imagine people will be able to do. I can imagine that maybe not right away, but someday we might have quantum computers that use light directly as compared to just as a tool to control something else. So we'll see. So no, I cannot predict the future.
But thank you. Thank you so much for your time, Dr. Mather. Signing off from Advanced Imaging and Optics Congress in Arlington, Virginia. Thank you.